Okay, so we have natural log of x equals the sum from n equals 1 to infinity times -1 to the n plus 1 times x minus 1 to the nth power over n. Okay, so we're just going to kind of tweak that a little bit. Okay. So what if we wanted to find natural log of x plus 1? All you have to do is replace x with x plus 1. So that means the natural log of x plus 1 is equal to the sum from n equals 1 to infinity of -1 to the n plus 1 times x plus 1 minus 1 to the nth power over n. Now, since the plus 1 and minus 1 cancel each other out, it's equal to sum from n equals 1 to infinity, -1 to the n plus 1 times x to the n divided by n. Okay. So let's say if we decided to find, kind of separate these a little bit, natural log of x squared plus 1. Same thing, we're just going to replace x with x squared plus 1. So our natural log of x squared plus 1, using this one, is equal to the sum from n equals 1 to infinity of -1 to the n plus 1 power times x squared plus 1 minus 1 to the nth power over n. Okay. And again, the plus and minus 1 cancel each other out. So that's equal to the sum from n equals 1 to infinity of -1 to the n plus 1 of x squared to the nth power over n. Or you can just make that x to the 2n power. -1 n plus 1 x to the 2n over n. So just from that natural log of x, you can play around with that a little bit each kind of way. So you may have natural log of x minus 1 or natural log of whatever. They'll twist it around all kinds of ways. All you have to do is replace that x in here, and that'll give you your new power series. All right. Now, some of the questions, they'll actually just give you the power series right from the beginning, so you don't have to do a whole lot of figuring out. Not all of them, but some. All right. So any questions on that one?
If this gives you the power series, would you just plug in the function inside of that for x? Like for that one, it has x squared plus 1 instead of the natural log. So you just plug that in for x in the normal function.
You mean for this one?
Yeah.
Oh, yep. Just plug it in into that x there. So when you plug it into that x there, it just automatically goes into that one. Any other questions on this? Yes.
Did you also apply that to the previous answers? With before we integrated the looking back at
Yeah, because I think I know what you're going to ask, and we're actually going to, if I'm thinking of the right question that you're going to ask, we're going to cover on the next example. Yeah. I know, I told you, it's something about that word that just itching for you to mess up on it. All right. Leave that up for a few more seconds. Actually, bring it up a little bit. right, so let's say for this example, use the power series. F of x equals natural log of 1 plus x, which equals the sum from n equals 1 to infinity of negative 1 to the n plus 1 power times xn over n from negative 1, between negative 1 and 1. To find a power series, I don't know why I get ready to say the. Power series representation for g of x, which equals 1 over 1 plus x on that same interval from negative 1 to 1. Okay. Now we know that our f of x is equal to natural log of 1 plus x, or x plus 1. And our g of x is equal to 1 over 1 plus x. Okay. So we can see that our g of x is just equal to f prime of x. So that means our g of x is equal to the derivative of f of x. So if it's the derivative of f of x, that's equal to the derivative of natural log of 1 plus x, which is equal to the sum from n equals 1 to infinity of negative 1 to the n plus 1 power times xn. Actually, I'll make that 1 over n times xn. Only because when you do the derivative and that n comes down, it'll cancel out. Okay, so we know that's going to equal the sum from n equal 1 to infinity of negative 1 to the n plus 1 power times, you don't have to put the times there, but just kind of separate it. You have 1 over n, that n comes down, times n x to the n minus 1. Okay, so we can see those two n's cancel out. So it's equal to the sum from n equals 1 to infinity of negative 1 to the n plus 1 power of x to the n minus 1. Yep, so that's your g of x. From negative 1 to 1. Uh-oh, put a comma there when I meant to put a less than. All right, so any questions on that one? All right, leave that up there for a few seconds. There we go. Okay, so for our next example, let's say if we use the power series representation, f of x equals natural log of 1 plus x squared. I have no idea why they do that on the example problems. They'll put the constant first and then the x term. But I try to write it the way it appears in the examples. In the questions. So from n equals 1 to infinity of -1 to the n plus 1 of x to the power of 2n over n. And we know that's from -1 to 1. Use that to find a power series representation for g of x is equal to 2x over 1 plus x squared. Again, from -1 to 1. Right. So you have the same thing here. You have your f of x, which is natural log of 1 plus x squared. And you have your g of x, which is 2x over 1 plus x squared. So we can see that our g of x is just equal to the derivative f prime of x. Well, derivative of natural log of 1 plus x squared, which is u prime over u. Okay, so that means your g of x is equal to, again, the derivative of f of x, which is the derivative of natural log of 1 plus x squared, which is the sum from n equals 1 to infinity of -1 to the n plus 1 power. And again, I'll just bring my 1 over n here times x to the 2n power. And I'll put that in parentheses just to separate it. And again, I only do that because this way when you bring down your 2n, the n's will cancel out. Okay. So this is going to equal the sum from n equals 1 to infinity of -1 to the n plus 1 of 1 over n. I'll go ahead and put the multiplication there, even though you don't have to. Bring down that 2n, so you have 2n times x to the 2n minus 1 times your u prime, which is 2. Okay, so again, these n's cancel out. So you have the sum from n equals 1 to infinity. Actually, you don't need that 2. I don't know what I'm thinking about. I don't know why I was thinking of e to the u. I have no idea why. I'm like, wait a minute, hold on. Yeah, that's why. So nope, you don't use that 2. -1 to the n plus 1. And if you want, you can bring the 2 here. You can leave it there. Doesn't really matter. You have 2x to the 2n minus 1. Actually, I did forget part of the problem. I drew an arrow right here so I wouldn't miss that part because I wrote it for some reason really light there. But I'll add it on to this one. Okay, so if you wanted to, you can make your 2x over 1 plus x squared equal the sum from n equals 1 to infinity of -1 times n plus 1. Oh, I meant to put my 2 right there. That's the whole reason I rewrote it. So that'd be 2 times -1 to the n plus 1. times x to the 2n minus 1. Yes.
Would you be able to bring the 2 outside of the sum?
Oh yeah, if you wanted to, you could bring it right out there. Okay. Now the part of the question that I forgot to write down, I'm trying to think if I have enough room. Yeah, I should have enough. Okay, and it said, find the value. We'll bring that up some more. Of the sum from n equals 1 to infinity of 2 times negative 1 to the n plus 1 times 1/3 to the power of 2n minus 1. Next time I'm going to highlight it so I don't miss that part. Okay. Now if you notice, the only difference between these two is just the fact that x is equal to 1/3. Okay, so we'll just let x equal 1/3, which means all we have to do is plug in 1/3 here, since they're equal. Okay, so that means g, I'll make that our g of x. So g of 1/3 is equal to 2 times 1/3 over 1 plus 1/3 squared. Which is 2/3 divided by 1 plus 1/9. If that's 9 over 9, that just becomes 10 over 9. So that's 2/3 divided by 10 over 9, which is 2/3 times 9 over 10, where that simplifies, and that simplifies. So you just get 3 over 5. All right, so any questions on that one? Yeah. So in your homework, you will actually see this as part of the original problem. Yes.
Will it always be like the same? Or are you not gonna have to manipulate that series?
What do you mean these series? You mean where
It's gonna
we?
be more than just the 1/3, so just the x.
Oh yeah, just the x value. Yep.
That's the only thing.
Yep. So the only thing is your series up here is going to change,
So is it?
and then your g of x is going to change, but there'll
is it
always
going to
be.
asking for what that value is, because doesn't that kind of give away the answer for the series representation?
It does, but they're kind of assuming you're going to go through the
Right.
steps of
Okay.
solving all that. So.
All right, just curious.
But a lot of the problems have it to where it's just find the power series representation.
Okay.
And then you
So
have
it's like
some.
two questions.
Exactly. So you're going to have some where you may have 10 where you have to do this.
So
And then you may have
couple.
10 that you have to do that, where you can kind of take that kind of shortcut. All right. Any other questions on this one? No. Yes.
Is there a way to go back from having the power series to the function?
To be honest, if I'm trying to think of the best way to do it, probably just the same steps in reverse. I'm trying as far as going back.
What does integrate?
Yeah, I'm thinking if we, since we
Use differential?
had the derivative, we integrated, it should take us back. As far as the procedure to go all the way back.
Like, would that take us back to the 2x over 1 plus x squared?
Oh, you mean this one?
Yeah.
Oh yeah, it should. Yeah, if you do the each term and then kind of convert it into a times r to the, is it n minus 1? Nope, it's just a to the rn. So once you put it into that form, then it takes you back to it. It all kind of starts with the geometric series. All right, any other questions? All right. Yep, there we go. Okay, so let's say, for example, we want to find the interval of convergence for the power series. The sum from n equals 1 to infinity of negative 1 to the n plus 1 over x to the n over n. Okay. So here we can just use the power, not the power series, the ratio test. I don't know why I keep saying that. Okay. So using the ratio test, which is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, where this is your a sub n. Okay, so this is going to equal, we can leave out the negative 1 since it's absolute value, we don't have to worry about that. The limit as n approaches infinity of a sub n plus 1 is x to the n plus 1 over n plus 1 divided by a sub n, which is just kind of the reciprocal of that if we multiply, times the n over x to the n. Okay. Which is going to equal the limit as n approaches infinity, our x to the n plus 1, that could just be x to the n times x to the first, or just x, over n plus 1 times n over x to the nth power, where those two are going to cancel out. Okay, so we'll pick it up over here. So we have the limit as n approaches infinity of the absolute value of x times n over n plus 1. Oh, shorten that up just a bit. Okay. So we can take this absolute value of x and just bring it out to the front. So you have absolute value of x times the limit as n approaches infinity. And if you have n over n plus 1, if you divide everything by n, you have n over n here, over n over n, you get 1 over 1, and that just approaches 0, so you end up with the absolute value of x. Okay, so we know that has to be less than 1 by the ratio test in order to converge. So a lot of times they'll give you this part where you don't have to use the ratio test, but this is just one of those, might as well get in a little extra practice. Okay. So we know that it converges because this is just negative 1 is less than x is less than 1. So we know it converges for negative 1, not equal to, less than x is less than 1. So the only thing we really have to do now is find the endpoints. See if it converge at negative 1 and 1. Okay. Now when x equals 1, if we plug it into our power series, you have the sum from n equals 1 to infinity of negative 1 to the n plus 1 times 1 to the power of n over n, which is just the sum from n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n. Okay. So because of that negative 1 to the n plus 1, we can't just use the p-series, which would be a whole lot easier. So we have to use the alternating series test. By the alternating series test, if you remember 1, the first step of it, the limit of a sub n as n approaches infinity has to equal 0. So we know this is equal to the limit as n approaches infinity of 1 over n, which is 0, so that one checks out. And for the second one, we know a sub n plus 1 has to be less than or equal to a sub n. So that means we have 1 over n plus 1 is less than or equal to 1 over n, which is also true. So we know it converges at x equals 1. Okay, so we got half of it down. Now we just have to plug in negative 1. X equals negative 1. Let me circle that one. Uh-oh, did I put 1 again?
Do it again.
I know, about to do the whole thing over again. There we go. Now for x equals negative 1, we have the sum from n equals 1 to infinity of negative 1 to the n plus 1 times negative 1 to the nth power over n. Okay. Now with this one, we have a negative 1 here, negative 1 here. We can just combine those two. Equals, n equals 1 to infinity of negative 1 to the n plus 1 plus n times 1 over n. Okay. So that gives us, if I pick it up on the next line, n equals 1 to infinity of negative 1 to the 2n plus 1 times 1 over n. Okay. So if we decide to separate those two, we can make that negative 1 to the 2n times negative 1 to the first power times 1 over n. Okay. So you have negative 1 raised to an even exponent. No matter what you plug in 1, it's going to be 2. You plug in 2, it's going to be 4. So this is always just going to be 1, no matter what value you plug in. So that's just 1. And this, negative 1 to the first power, is just negative 1. So that gives us, let me bring that up some, the sum from n equals 1 to infinity of negative 1 over n, or you can write it as 1 over n and bring the negative out to the front. Okay. So now you can use the p-series test. Okay. So by the p-series, this diverges. So, put the negative sum from n equals 1 to infinity of 1 over n to the first power diverges simply because your p is less than or equal to 1.